Let's have a look-see at the Proxxon FF230 Mini Micro Nano. I have no idea what size category this is. This mill fits into. You know, most micro mills that you can get are in the flyweight category at about 100 pounds thereabouts. This tiny little mill comes in at around a toddler weight of about 40 pounds. It is really dinky. Maybe that's its category. Maybe it's a dinky class. Well, I'm probably wrong about that. Just as I'm wrong about what the FF and FF230 stands for. I'm pretty sure that in reality it's got to be something meaningful in German. Made in Germany. That is one of the reasons why I got this little tiny mill. There's a lot of other mills on the market, heavier. I got this for two reasons. First of all, it is so small and light I can pick it up and I can put it away on my cupboard. I can put it away. Try doing that at the end of the evening with a 100-pound or 150-pound mill. No way. Yeah, one reason, it's lightweight. The second reason is that it is made in Germany. I kind of like that because I am a complete noob at this. But when I got this mill, I never milled before or anything. And, well, I guess that goes without saying because any real machinist is going to get a big machine. But if you're going to spend money on a machine, you don't want to get a dud. And that can happen if you go with a cheap import. A great channel, Adventures with a Small Lathe. In fact, that's the channel that got me interested in machining in the first place. Great job, thanks man. He uses a FF230 machine. And in recent times, he got himself a very inexpensive import lathe. And it looks like an absolute disaster. The machine just has nothing but problems, and he's having a hoot. He's having a hoot and a holler getting that thing working, but for a noob, it looks like trouble. On the other hand, this FF230 made in Germany, like, it has a really nice fit and finish. All the tolerances are pretty decent. I knew ahead of time that I'd be getting something that, well, at least it'd give me a little bit of a head start, and I'm not going to have any major headaches. Of course, the machine has limitations, and that's what this video series is going to be about. It's going to have to be a video series. Ordinarily, I do a look-see in one video, but with this, no way. This is going to require a lot of discussion. I figure I'm going to need 3 videos to do this. The first video is, well, what I'm doing right now is just a really quick go over my general thoughts and feelings about the machine. But mainly this video, I'd like to talk about what I believe is this machine's best asset, and that would be the table. So the table will be the first topic of discussion this video. The next video, when that'll come out, I don't know, because I have lots of ideas of things I'd like to also work on. But my next video on this machine will be to do with the Z-axis. The column block, the quill block, the quill, and the business end of the spindle. And that's where this machine, it has some limitations. The table's wonderful, however, there's some run-out issues and there's some wobbly issues. I have some ideas as to what's causing them, and maybe we can work that out in the next video. And then in the third video, I'd like to come back and look at the motor head of the machine and take a look at just how many RPMs this thing puts out, and maybe dive into the electronics in the motor and the motor mount and stuff like that, and see if there's any possibility for future upgrade and I'll be on that sort of a topic. Anyways, stick around and let's have a first look at this machine. Okay, let's start off with the basics. This here is a milling machine. What it means is that it looks a little bit like a drill press, but it's not exactly. It looks like a drill press because it has a thing on it that spins and you can put drill bits in it. But how it differs is that it is designed to withstand horizontal loads. So you can take a chunk of metal and you can ram it into a bit, and the bit can cut away your workpiece, and you machine. You can take a big chunk of metal and you can create your dreams. machining is such a cool hobby. Anyways, this machine, it stands about 20 inches high as it's set up at the moment. If the motor's all the way raised up to the top, it's about 24, 25 inches high, and that leaves around 8 inches of working distance here on the Z-axis between the collet holder and the table. The table itself is roughly about a little more than 10.5 inches long, and it's about 3 inches wide. This machine, this size class of machine, there's not very many of them made. In fact, the only one I could find that is directly comparable would be the machines by Shurline. Shurline is a pretty cool company. All made in the United States. They look beautiful. They really look awesome. And they have an extensive ecosystem, all sorts of parts available and all sorts of additions. It's very configurable. But the problem with the Shurline that held me off and made me go to this Proxxon instead is that it is entirely aluminum. And because of that, possibly because of that, a lot of people on the internet said that it's just not really suitable for machining steel. Yeah, if you have a Shurline and you find that it's actually not the case, let me know. I'd be very interested. But yeah, this Proxxon, on the other hand, it's all cast iron and steel, and it's really solid. I've already done a number of machining tasks, and you can check out my YouTube channel and find some of my videos where I machine stainless steel and aluminum and a bunch of other stuff. Yeah, this machine's pretty capable. It has some shortcomings. We'll explore those in today's video and the future videos I make in the future. One of the shortcomings, though, in my opinion, is that it does not have an extensive ecosystem of parts available. There's some. I got most of them now, and well, you'll just subscribe and you'll see them eventually in action. Anyways, let's begin the video proper with a look at what I consider to be the best part of this machine. Let's have a deep dive into the table. What I am going to do is take it apart in front of you so you can see what's inside it, and then I'd like to put it back together and tune it. And I will use after that a test indicator to figure out just how much slop is in this table. I can give you a preview. It's not a lot. This table's really nice and accurate. The rest of the machine, well, future videos. Anyways, let's move forward. Let's start off with the rear, where my eye is naturally drawn. What we find is that the table has about a 45 millimeter overhang into which the column is inserted into a bore. The column is about 35 millimeters in diameter, and I understand that it is stopped down in the bore. Well, we'll check that out in a moment. So the column is at the back of the table, and when the table is in its fully inward position, the column is what's blocking the table from going any further. The front faceplate of the mill also would, I'm not quite sure which is the limiting factor. The tolerances are pretty good. In fact, could be both of them are limiting the in-travel in the y-axis. Well, one thing that drew me to this table that I thought was pretty cool is that it seems to be inherently swarf resistant. A lot of machine tables have the lead screw exposed, and you need a bellows to prevent any of the swarf from getting onto the lead screw and then gumming up the works. And well, the lead screws, if that happens, they won't last as long. Anyways, we'll test this and keep special attention to all the little swarf bits, because I haven't given this machine a good proper cleaning for quite a few projects. I've machined stainless steel for the Shoeless Traveler 2.0 and a whole bunch of aluminum for a couple other projects. So keep your eye on that. Let's see whether the innards really are free of swarf or not. What you see over the lead screw well is a plate, and the plate is keeping the swarf out. The plate's a little bit annoying to get in and out of the machine. I find one of these magnets to be quite helpful in that regard. Let's take a look in there. Yeah, it's pretty clean. It's not bad at all. There's a few little chips at the bottom, but not too bad. Anyways, let's roll this table back in and take the column off. Okay, I got a hex key here, and there's one. Get the second set screw out. By using set screws and having a round column, it allows the milling head to be oriented in any number of directions. You can even reverse it completely and use it as a drilling machine for large surfaces. I actually did that in that video where I finished this workbench. You can check out that. Here comes the column, and let's just check out the dimensions of that inner bore. It's being scored up by those set screws pretty badly. That's why it didn't come out as smoothly as it went in. And we have a bore of 34 millimeters, so it's a 1 millimeter step down. Set that aside. And what's left here is the table proper. This is the KT230 table, and you could buy this separately if you want to roll your own milling setup. And with that 34 millimeter bore, you might be able to think up of some sort of alternative Z-axis and motor unit. Anyway, let's take it apart and see what makes it work. First of all, here's this little ruler thing. This table is heavy. It's the majority of the weight of the machine. This ruler is absolutely useless. I have no idea why they include that, because it's so low in resolution. It just slides out the end like that. In fact, I have an idea to use that slot for some project in the future, and this thing I'll just go into the box, into the storage box, I suppose. All right, let's roll this unit off, take the table apart, and just move that to the very end. But when I set it back up again, I'll do some measurements of just exactly how much travel it has, because it actually has a little bit more than advertised. The advertised amount of travel's on the conservative side. I think it's off the lead screw now. It is, but something is blocking it from going any further. And I think that it is a bolt. Geez, that's heavy. I think it's one of these bolts. I think it's that one right there. So let's see if we release that. I'll just open that up a bit. And well, I have it upside down. Let's just take a look in there. And you can see there is a little bit of swarf buildup underneath on those guides. That's interesting. Now I got a bunch of swarf on my table. I'm going to get some of that embedded in my hands, notably. Okay, that should come off now. Yeah, it comes off. You got a feeler gauge here. There it is. And you can see some of the swarf left on that. But that's not actually a guiding surface. However, this here, this flat down here and on the other side, that as well as the in part of this dovetail, that's the actual surface onto which this is riding. Okay, now we can continue pulling this table off. And once again, this table is, for such a small device, this table's pretty massive. It's solid cast iron, and I'm getting chips all over myself now. Anyways, here is the inside of the machine, and you see that the guiding surface has a nice film of oil, and it's kind of dirty, but there's no swarf there. The swarf is on the upper flat, but that flat's not actually making any sort of contact with that flat. Anyways, let me put that down. And I know what, wipe my hands off, and I'm going to continue disassembling this. Hold on. Before I proceed any further, I'm going to give this table a good cleaning, because it has these little stainless steel dagger needles that are really, really irritating on the skin. So I want to give this a good cleaning before we continue onwards. I think I'm going to do some of this off of camera. Now that was a royal pain in the ass. The reason being is that Proxxon has opted to use grease for lubricating the lead screw. This is the protector plate that prevents any chips from getting on the Y-axis lead screw, but the slide, the Y-axis slide would, in its in and out action, would eventually plow the chips, and they'd fall off of this protective plate, and they'd end up on the lead screw there. I don't think it was a huge issue, because there was a big wad of grease around around this area, and all the chips seemed to be on the outside of it. Nonetheless, I think that would be a good idea to give the machine a really thorough tear down and cleaning at least once or twice a year. I always thought that it might be an interesting experiment to manufacture one of my own lead screw nuts. Brass, it looks like it's, the mill, it's supposed to be the machine that could completely replace itself. I'm not entirely sure about the Proxxon FF230, but at the very least it should be able to fabricate a new one of these. And I always thought it might be an interesting experiment to try making my own lead screw nuts, a little bit of a different configuration, and possibly with an oil well that would give a very, very slow dribble of oil to the lead screw inside the nut, and that might help flush away chips. I'm not sure I'll ever actually do that. It seems like it's more effort than is really necessary, and I'm not sure whether it would cause any sort of additional headaches that I don't foresee. Yeah, the grease, it works pretty well. The hand action's pretty smooth. The lead screw spins quite nice and freely. You notice that it's split, and with the split you can tension this nut and adjust it, and you can get the feel just right and really minimize the play. We'll examine that shortly. Anyways, there's the lead screw nut, and some other user-makeable, replaceable parts would be these brass jibs. Fairly simple structures. We got one here for the x-axis, another one for the y-axis. Here is the y-axis lead screw, and a couple things to note about it. First of all, it doesn't have anything special for how it is being held in place. I don't think it really needs anything more than this thin washer. It fits into this faceplate, which I'm actually kind of amazed with. It's actually steel, a magnet. Yeah, it's actually steel, but it's machined so nicely and blackened so well it almost looks like anodized aluminum. So they did a really good job on that. Anyways, the lead screw fits into these face plates, and you put another washer on the other end, and the hand wheel simply screws on like that. Now, one thing I would like to mention in the video is when I did get this mill in the mail, it had been dropped. The UPS delivery dude, he dropped it, and the styrofoam padding at the base of the mill was all crushed in on one side. Unsurprising, considering just how bloody dense this little mill is. Only 42 pounds, but it's in the area not much bigger than your forearm. And what happened is this table shifted in the box. The styrofoam padding gave, and notice that thin area right there? it completely bent both the X and the Y lead screws, and I had to contact Proxxon. And to their credit, they were quite helpful. They were like, no problem, we'll send you out some new lead screws, and I got them within a week or two. So that was very nice of them. Yeah, but you're gonna want to be careful with this mill, just because of the density of this base. It's a bit of a weak point that could easily be damaged. And when that did happen, it made the hand wheel action very poor, because the hand wheel wasn't sitting on nice and straight. Yeah, this table, I'm still really impressed with this, at least this part of the mill. Cast iron, it's got to weigh over 10 pounds, that table. And cast iron base, cast iron, steel, brass, aluminum. The hand wheel's the only aluminum part. Even the knob is very nicely turned steel. Here is the graduated ring, and it differs a little bit from the parts diagram. The parts diagram shows a spring, some sort of little metallic leaf spring to hold this in and to give it a little bit of stiction from moving. Anyways, that's all there is to it, and all there is to do now is to put it back together and to try optimizing it, try to reduce play as much as possible. I think I might do some of this off camera, and I'll do some of it. I'll record what I'm doing and show you some salient tidbits of putting it back together. Anyways, I'll leave the camera rolling. One thing I learned the last time I disassembled this table is leave the lead screw nuts a little bit loose, and you gotta tighten them up at the end, because they do have a little bit of wiggle room, and that wiggle room needs to be, well, it needs to accommodate proper tracking. Now, similarly, these face plates should only be lightly tightened at this point. There's still some play. Dabble, do you? Before I put the Y-axis back on, notice that there is a through hole. I wonder what that one is for. Well, once you get this assembled and it's lined up proper, it allows the play in the X nut to be tightened down or adjusted. This jib fits in like so. Notice that this jib is the full length. It runs the full length of the Y-axis. That would be along here. However, the Y-axis, over its entire length, that jib is not always making full engagement with the base of the mill. And that does, I have found, make it rather difficult for adjusting the play in this mill. And hopefully now it works. Getting these jibs adjusted just right is a very tedious process. Okay, that should work better now. Okay, engage you nut. So getting this to fit back is not super straightforward. Okay, there we go. Now, the trick to getting all of those screws tightened to get optimum performance is you tighten them after the Y table is maximally in, and you might need to dick around with it a little bit to get it really working nicely. A little bit tight there. little bit tight there. Yeah, not bad. Okay, now I got the Y nut and faceplate on straight. I can tighten it down good. The other one down. But I'm going to leave the Y nut adjust until the last thing I do. For now, what I like to take care of is the Y jib, and as you can see, or hear, it is not adjusted properly. This Y jib, I find it very annoying to get down to exactly where I want it to be. And why I find it annoying, other than not having the right hex key on hand, is that it's that when you get these set screws just to the right level and you use the lock nuts invariably end up tightening the set screw as well. And it's a little bit annoying. So what I do is just this very, very tedious back and forth of just getting these things slightly tight, getting these nuts just slightly tight, and how's that? Not bad, not bad. That's about right. But no play. But when I go to tighten up these lock nuts, well, let's see what happens. Yeah, it's a lot tighter now. Not terrible. I'm going to have to off camera play around with it a bit and try to get these set screws just right. But before I put that X table back on top, I'd like to mention a little bit more about this jib. Like I said earlier, the jib is not always making full contact with the base, and it has an interesting effect. And the effect is that when the Y table is maximally inwardly traveled, like, well, maybe not maximum, but getting close, that jib is making full contact, and this table is really, really solid. However, when this table is extended out to getting close to where its maximum travel would be, well, now there's a lot less jib making contact with the base, and we're going to have to test that later with the dial indicator, and I can feel right now that there is a little bit of play in the table. I kind of wonder, maybe one of these days it'll be a project of mine, because I don't want to ruin this jib that came with the mill, to make a new one, but instead of full length, to make a jib that's only the length of these 3 screws. And that way, it might sacrifice a little bit of stability when the Y table is maximally in, but it would make it more consistent when the table is at maximum extension. At least then that jib is still and mostly in full contact with the base, and that way I can get these set screws tightened up a little bit better. As it stands, I find there's a little bit of a trade-off. If it's tightened up so that it gets little play when the table's extended, then it's too tight to actually draw the table all the way into the column, all the way forward. These jib screws really are a pain in the ass to get set up nicely. What I find to work usually fairly well is to get it to the point tightened till you can just begin to feel resistance. Back off a tiny amount and then tighten the lock screw, and you'll see that it actually does tighten the little set screw as well. So it does add a little bit more clamping force, and usually that gives a fairly good feel, and it's a good compromise for stability. You know, if there's no play whatsoever, well, it ain't gonna move, and you do want it to move smoothly. Okay, I'm gonna put the column back on and set it up for some measurements. No, I almost forgot, I gotta tighten up this Y-axis lead screw nut. And once again, you do not want it to be too tight, otherwise you're going to be prematurely wearing that nut out. You just want it to the point that it is barely tightening, and then loosen it up just a touch. Okay, that should be good. Alright, now let's run some tests. I keep forgetting all the adjustments you need to make before the table works proper. The last one is the hand wheel play. At the moment it's not locked down. So what I do is I get it locked like this. So now this hand wheels is locked against the faceplate, and back it off less than 0.05 of a millimeter, and give it a test. No, that's still a little bit too tight. Back it off just a little bit more. Yeah, that's about right. So that should minimize play. Now let's do some tests. Okay, the first test is just how tight those jibs are set. And at the moment, notice that the y-axis is all the way retracted in. The x-axis, it shouldn't really matter because that jib is making contact along the folding. So I'm just going to test it in two positions. Table Y retracted and table Y out. I don't have the mill bolted down, so if the mill wobbles around, that's not anything. Just pay attention to the dial indicator. Let me get it nice and zeroed, and let's just see how much play I can induce. You see, it's not a lot. It's less than, oh, that's maybe about maybe 2/100ths of a millimeter that way and 1/100ths of a millimeter that way. However, is that going to play out the same amount when this table, when the Y is fully extended? And I don't think that would be the case whatsoever. So that is about its maximum extent. Let's get the dial indicator repositioned. I would say that's about the play there. Let's try to center that. Yeah, it's about twice the amount of play, almost a full 1/10 of a millimeter. That's again with the y-axis fully extended. Oh, that should thereabouts get it. And you get that hand wheel, you get the dial indicator zeroed. Put the hand wheel at exactly, let's see here. Okay, I'm moving forward. And I have that zeroed and I have that zeroed. Now let me reverse the direction and see how much the hand wheel moves before that test indicator budges. Oh, I can feel the stiction there. That is, I can feel the resistance. That's about 0.07 millimeters before that indicator actually moves. So that's 0.07 millimeters of of slop on the y-axis. Now let's set it up for testing the x-axis. I get the hand wheel zeroed. Hopefully the camera's not picking up too many reflections. Oh, try that again. Get the hand wheel zeroed, and then get the test indicator zeroed. Now pay special attention to the hand wheel and see how much it moves before the test indicator moves. That's 5/100ths of a millimeter, 6/100ths, and there we go. So in both axes, I got 0.07 of a millimeter on the y and 0.06 of a millimeter on the x-axis. Not too bad at all, not shabby. Okay, let's measure travel that this table has. Proxxon claims that has 170 millimeters of travel on the x-axis and 65 millimeters of travel on the y-axis. I'm pretty sure that they get those numbers from the length of the lead screws, the x and the y lead screws. However, because the lead screws make engagement with the nut and you got these dovetails, the actual values are a little bit different, I find, practically than those stated values. For instance, the x-axis, I have it all the way skewed to the right. However, it is still making full engagement with this Y-sled dovetail. And I'm not going to show you, but in there, the lead screw is still in the nut. So we can measure the usable x-axis travel from the Y-sled to this X faceplate just by sticking a ruler up like that, and we come up with 173 millimeters. So yeah, 173 millimeters of useful travel. And if you want to be a little bit risky with your machining, you could get even a little bit more. Let's just find out where it finally disengages with the x-axis nut. It's around there, and we find that we have almost an extra 16 millimeters of travel before the lead screw finally disengages. It's not making full contact with the dovetail, so stability will be a little bit more shaky. But, well, depending on what you're doing, it could be useful having that extra little bit of a distance. Now let's check out the y-axis. The y-axis, recall, its limiting inward travel is the column or the y faceplate. They're both very similar. So we can simply measure from the back of the table to the column, and that'll give us the travel. Let's start off with a conservative measurement, and here I have the table in line with the front of the base, and that would mean that this table's making full engagement with the Y dovetail. And stick the ruler up to the column, and what we find is that it's a little bit less actually than what Proxxon states. It looks to me like it's about 61, maybe 62 millimeters, and that's it. However, that's the conservative view of things. We can see whether that lead screw is... It's already well in the nut, actually. I can feel with my finger back there. Let's just roll the Y table all the way off the lead screw, and that'll give us a rough estimate of... There we go. Now let's just push it back in, and that would be the absolute maximum Y travel, and it's getting really risky when you're going that far out. The absolute Y travel is about 70 millimeters. So yeah, X and Y. X 173 usable, 100 and maybe 78, 79, and being a bit risky. Y 65 is actually probably realistic, and going any further than 65, you're really pulling that Y sled a little too far out. And not only that, don't forget that it is get a lot more shaky as you pull this Y-sled out. Well, that finishes up our look-see at the FF230 Mill, at least the first part of what will be a series of videos. We just looked at the KT230 table, and I hope that I covered it in inadequate detail. In case I missed anything, let me know in the comments below, and otherwise, thanks for watching, take care, subscribe, and I'll hopefully get another video out on the Z-axis in short order. Bye-bye.